Hello. First of all, thank you for attending this presentation. My name is Pablo Fuentes, and here I will introduce UCDebug. UCDebug, I will move so you can see better. UCDebug is a debugging tool for ARM assembly code in RISC OS running over Raspberry Pi. But before I explain what you can do with UCDebug, I would like to briefly mention where does the project come from. This tool has been developed at the University of Cantabaria, which I expect most of you haven't heard of before or can't really place in the map. Well, obviously it's in Spain, more concretely in the north of Spain, where there is a city called Santander, which probably will ring you a bell because of the bank. So therein lies most of the University of Cantabria, which is a small, relatively small, yet modern university. The official figures from 2 years ago show that we had a bit less than 12,000 students, and we were, in terms of size, roughly below the national average. However, we have a rich and varied amount of offer of studies with 32 degrees, 44 masters, 20 PhD programs. And one of the centers in the University of Cantabria is the Faculty of Science, which is where I come from. There, apart from also several masters and one PhD program, we offer 4 different degrees. And I want to highlight the degree in computer science, in which I teach, because it is considered, it is ranked among the best in Spain, both in terms of teaching quality and research. So, in this faculty is placed our group, the Computer Architecture and Technology Group, or ATC by Spanish acronym, which is also a small group composed by 13 people, comprising professors, and postdoc researchers, and PhD students. And there we have 4 different main lines of research, focusing on interconnection networks, on task-oriented programming models, and the use of GPUs and other accelerators to improve the performance of applications. From these people, the UC tool was born from 4 of us, professors Carmen Martinez, Fernando Vallejo, and postdoc researcher Cristobal Camarero, and myself. And why did we develop UCDebug? Well, as I mentioned, we teach in the degree of computer science, where some of the courses that we give are focused on computer structure and organization. Those courses are mandatory and are taken by roughly 400 people per year. In those courses, we follow an architecture of reference, and we used to employ MIPS. However, MIPS is not very common anymore, which had a problem because students did not think it was important, and also because the practical sessions were tackled very much to our lab. So, to fix this, because this led to 2 big problems, that our students lack motivation and they withdraw from the courses. And to fix this, we launched 5 years ago a series of innovation projects in which we found 2 keystones. First, we could switch to ARM as an architecture of reference, which is still RISC, but it's more widespread. Here, I'm sure everyone has a mobile phone with an ARM processor, probably a tablet with an ARM processor, maybe even a laptop. So this made it that it had more sense for our students to learn that. And also, we decided that we could switch to the Raspberry Pi for our practical sessions. And why the Raspberry Pi? Well, we were looking for 2 main targets: low price and widespread availability, so that our students could work at home and improve their autonomous work if they so desired. And we were also looking for a device that had a rich ecosystem of simple input-output devices that could be used in our practical sessions. And this basically left us with 2 options: Arduino and Raspberry Pi. However, we also wanted a device that could run standalone with running a modern OS, so that we didn't need a PC attached to it, and that ruled Arduino out of the question. And among the Raspberry Pi devices, we chose the 1B Plus model because it was the latest available with a monocore processor, which removed the interference from having multiple cores running, which can be a bit more difficult for a student to learn. And also because it had very comprehensive documentation for its processor. So we had already chosen the platform, but we needed an OS. And we selected RISC OS. Surprise! So, why RISC OS? Well, we wanted something with a visual interface. There's no point in removing the PC attached to the device if you are linked to forced to use an ugly prompt with only letters. And we wanted also an OS that allowed us to to employ input-output devices with very low interference from the system. So RISC OS was a perfect match for that. Additionally, we found that the GCC toolchain was already available in RISC OS, which was great because that made it more probable that our students had both already used it before and that they would reuse it again in future courses. So it made sense. But we also needed a debugging tool. And that's where the problem came from. We evaluated 4 different alternatives: the GDB debugger, the native RISC OS debugger, DDT, and Breakade. However, GDB was, it's a very common tool, it's available in most OSs, but we could not make it work in RISC OS running over the Raspberry Pi. So, there you go. The native RISC OS debugger is a very powerful tool, very useful, but does not have the most intuitive or user-friendly interface. And we wanted something that had a GUI so the students could easily learn how to use it. DDT had a paid license, which did not make it the best option for the students to work at home. And finally, Breakade required to preset the breakpoints. And when you're learning to code in any architecture, most probably, and even more for a student, most probably you don't know where you should be placing those breakpoints. So we needed something else. And that's why we developed UCDebug. Mainly with the target of using it in our teaching courses, but inspired by professional debuggers such as the OLIDBG in Windows. Here's the default view that you see when you start the UCDebugger, the UCDebug debugger. It is composed by 4 different windows, plus an icon here at the right of the icon bar, where there is a hidden menu that you can use to select additional options. The first window that we have is the console view, where you can input simple commands to load a user program, run and stop its execution, and even change the values in the memory or the registers, if you so desire. The second window shows the instructions in the user code. In this, both in machine code, machine instructions, and in ARM assembly. In this window, if you click with the mouse wheel over any instruction, it toggles a breakpoint, places or removes it. Whenever a breakpoint is placed at an instruction, that instruction is highlighted in red so that the user can easily know where the execution will stop. The third window shows the contents of the memory in organized by lines of 4 words per line. By default, the view is in words, but clicking with the mouse wheel, you can switch to half words or bytes. Finally, the fourth window shows the contents of the general bank of registers, plus the CPSR, and separate views for the flags in the CPSR and the CPU mode, so that the user can easily know at what point of the execution it is and what is exactly the machine doing. Additionally, there's a view for the SPSR register, which is engraved and shows its content when you are running a program in a CPU mode that has this register. So what we do in our practical sessions what our students do in our practical sessions with UCDebug is, first, they code their programs in RISC OS using the strong ED editor. When they have done that, they assemble and link them so that they can be loaded in UCDebug through the GCC toolchain, and specifying a concrete entry point so that they can be loaded to the UCDebug tool. And what happens when you do so? Well, first of all, when you load a code, obviously the contents of the user instructions and the memory view are updated to reflect that the program has been loaded. Also, the instruction shown at the very beginning of the code window corresponds to the instruction at the entry point of the user program. You can see also that the program counter has been updated to show the address of this entry point. You can also see that it is highlighted, this should be green, by the way, and that at any point during the execution of a user program, UCDebug shows in green the instruction that will be executed next. If from there on, we can execute a single instruction, and if we do so, you can see that the content, well, it is a bit more difficult to appreciate it, but the content of the first register has changed. And at any point of the execution, at any point that the execution stops, UCDebug highlights in red those registers whose content has changed in the meantime, so that the user can know what has changed, what has happened. We can also execute the whole code, and it will only stop if it reaches a breakpoint, if the program ends normally, or if there is an error, like is the case here. If that happens, UCDebug will show a message highlighting at which address did the problem occur. UCDebug also allows to read or print from the standard input and output. And at when a user code tries to read or print from the user input or output, it will open a separate window where the messages printed by the user program are shown, so that the user can easily separate what has been shown, what has been printed by the user program from the comments he or she is using. So, what can you do with UCDebug? UCDebug is able to debug simple programs. It can handle arithmetic operations both in integer and floating point. If you want to do so, you can open a separate window to see the contents of the floating point registers by using the menu at the icon bar. Obviously, it can handle function calls, and it captures certain software interrupts. Some make sense. For example, if you want to print or read from the standard input or output, the UCDebug tool needs to know that it has to open this window that I showed. But also some other software interrupts, like those that place or remove a handler for an interrupt. Because UCDebug is also able to handle interrupts. And when a user program places a handler for an interrupt, and that interrupt occurs during the execution of the user program, the control of the execution goes to that handler, and if the user has placed a breakpoint at that handler in the tool, or if there is an error, the execution will stop there, and the user will be able to know what's going on. An additional benefit of this tool is that it has been extensively tested. Remember that I said that we had around 400 students a year taking those courses. That, by the way, means that we have around 400 people using RISC OS. So it is making for a sizable community in Spain, I think. Let's hope that they start to join the community a bit tighter. But it also means that they have been using the tool. So they've been able to find several errors, many bugs in the code. Most of them have been already fixed. A few remain, but they are minor bugs and they are well documented, so you can easily check if the tool will suit your needs or not. So, and for more detail about what you can do with the UCDebug tool, I would like to invite you to later on join me at the stand at the corner in the outside, so you can see with your own eyes what you can do with the tool. So finally, how do we see the future? Well, first of all, we're trying to fix those minor bugs that I mentioned. We are working on releasing proper documentation, because the one we have now is a bit lacking. We have also in the cards to make a new video with a tutorial for the tool, this time in English. And we have also identified a characteristic behavior of the UCDebug tool, and it is that the execution time of a user program in the tool, in the debugger, increases by an order of 4 degrees of magnitude. Most of the time, this is not a problem. The execution time that you see with the tool is relatively fast, so you don't really notice. But it can be an issue when you are handling input-output devices with time constraints that are lower than those 4 degrees of magnitude. And for that reason, we are developing a go fast mode, which significantly reduces that overhead, but it is currently in beta mode. A student is working on that, and we expect it to be fully released within this year or the following one. And we are trying to pitch this tool to universities, both in Spain and abroad. So if any of you know someone in academia that you think may help them this tool, please send them the link, forward them to the repo so they can check by themselves. But we also would like to, for many other people that are not in academia, to use it. However, we know that certain features are not in our critical path, and it's very difficult for us to justify the time to fix them or to develop them. So that's why we released this tool as an open source software project, so that anyone can tweak it and make it work for their use case, and hopefully make the tool more useful for everyone and more used as well. And finally, I would like for you to chime in and tell me what you think the future holds for the relationship between RISC OS and the Raspberry Pi. As we all know, the latest Pi model, the P4, was released a few months ago, and I think we have not yet a running RISC OS version for that device. But I would like to know, how do you think the future holds? How far the relationship you think can go? Because, well, for now on, we are very tied to this device, to the Raspberry Pi. But before ending, I would like to thank the University of Cantabria for supporting and funding this project. The 4 students that have worked in our innovation projects, particularly David Herreros, which is a student currently working on the development of this Go Fast mode. And finally, all the students that have employed the tool and have helped us find the bugs on it. Thanks for your attention.
Is there a trace facility in the debugger so you can log what instructions the debugger actually went through?
No. You can execute, you can, for example, you can decide which amount of, you can, for example, make the debugger only run an amount of instructions. I think you can place a breakpoint and tell it to run up to that point, or from a point on, but you cannot really go back in time and see what the execution has gone through.
So no. It doesn't like log the instructions that it ran through into a file or something like this?
No. Currently, no. It could be done, because I tried to keep the technical details at the minimum, but feel free to ask. And what it does is it only executes an instruction from the user program at a time. That's why the overhead is so big. But this allows us to do, for example, what you say, print in a trace file what the instructions that have been performed and the contents of, I don't know, the memory, the bank of registers, so someone can go back and see where the problems came. Yes.
Yeah, I've done some development with different assemblers, and I find that if you're tracing through 10,000 instructions, it's good to just have the log and then bisect through the log. You know, it's in the first half of that. It's in the first half of that. And so yeah, I've found that logging is very helpful in such debugging.
It's a great idea, and I think this shows some of the differences that may be between the academia world and what a developer can be doing. So for a student, this is not something that is usually necessary, but can be incredibly useful for a developer. So thanks for asking. Thank you.
Did you have to write documentation for RISC OS for the students so they knew how to use that to start with?
Not really. We made a series of video tutorials that are on YouTube so that they could learn the basic use of the interface. I think once you overcome the first impression that everything is different from Windows, it is in fact quite easily to use. I mean, you only just have to change your mind and think, okay, what I usually do with the right button of the mouse should probably go with a click wheel, and no, with that. And we also think that it's a good opportunity for our students to learn different OSs that do not perform as they expect, so that they can have a more open mind. But no, apart from the videos, no.
Does it run on all RISC OS machines, or is it just limited to the Pi?
Currently, it runs on the Pi. We have tested it mostly in the 1B+. We have also run a few tests on the P2 and 3, and apparently it works. But since we have not made as many tests as with the 1B+, we still say that it's in beta mode. For other machines, there is some major hindrance, and it is that we don't have them. But so that makes it a bit difficult. In theory, it should work, making a few tweaks on the code, because what it does is that it checks the processor to know where what the address for the controller will be, and there it distinguishes between the 1B+ and alike models, for example the 0, or the 2 and 3. But if you tweak those few lines, which are relatively few and in C code, so they are easy to find, it should work. But if you're interested, if any of you are interested, please have a look at the code. Feel free to send to shoot us an email with any questions that you have, so that we can make it work.